current electricity for class 12. Hi, myself Dr. S.K. Bushya, former HOD, Department of Physics, Cotton University. This is a video lecture in physics for class 12 students. Lesson 4 of chapter 3, in which we'll learn about combination of electrical cells. Let's begin. A number of cells may be connected in a circuit as a combination. There are two basic combinations of cells, namely the series combination and the parallel combination. We are interested in finding an equivalent cell to a given combination. First, the series combination of two cells. Two cells are said to be connected in series if they occur one after another along a single path. In this arrangement, the negative of one cell is connected to the positive of the other. In the figure, two cells of EMFs E1 and E2, where E1 is greater than E2, say, and internal resistances R1 and R2, respectively, are connected in series between the points A and C of a circuit. The current flows from C to A, and let it be I. Let VA, VB, and VC be the potentials of the points A, B, and C of the circuit, respectively. Now, VA minus VB, which is equal to terminal PD or potential difference across the first cell, is equal to E1 minus IR1. This is equation 1. And VB minus VC equal to terminal PD across the second cell is equal to E2 minus IR2. This is equation 2. Now, the PD between A and C can be expressed as VA minus VC equal to within bracket VA minus VB plus within bracket VB minus VC. Now substituting equations 1 and 2, VA minus VC is equal to E1 minus IR1 plus E2 minus IR2, which is equal to within bracket E1 plus E2 minus I into within bracket R1 plus R2. We call it equation 3. The combination of the cells between A and C is now replaced with its equivalent cell of EMF E and internal resistance R. Equivalence demands that the same current I flows through it, and also the PD across A and C in the equivalent circuit and that in the original circuit must be identical. Now, the PD across A and C in the equivalent circuit is given by VA minus VC, which is equal to terminal PD across the equivalent cell, is equal to E minus IR. It is equation 4. Comparing equations 3 and 4, we get E equal to E1 plus E2. We call it equation 5. And R equal to R1 plus R2. We call it equation 6. Equation 5 and 6 give the equivalent EMF and the equivalent resistance, respectively. In the combination, the negative of the first cell has been connected to the positive of the second. If instead, had we connected the two negatives as in the adjoining figure, the equation 2 would have changed to VV minus VC equal to minus E2 minus I dash R. This is equation 7. This would have given E equal to E1 minus E2 as E1 is greater than E2. We call it equation 8. And obviously, because the cells are connected in the reverse order, current will change from I to I dash, say. Equation 6 for R, however, remains valid as the resistance does not depend on the direction of the current. Now, series combination of N cells. It is straightforward to extend the equations 5 and 6 to a series combination of N cells of EMFs E1, E2, up to En, and internal resistances R1, R2, up to Rn respectively. The equivalent EMF E and the equivalent internal resistance R are respectively given by E equal to E1 plus E2 plus up to En. This is equation 9. And R equal to R1 plus R2 plus up to Rn. This is equation 10. Remark. Equation 9 is valid if the current emerges from the positive terminal of each cell in the combination. If the current happens to emerge from the negative terminal of a cell, then the EMF of that cell enters the equation 9 with a negative sign. Equation 10, however, is maintained as the resistance is independent of the direction of the current. Now come to parallel combination of two cells. Two cells are said to be connected in parallel between 2 points A and B of a circuit if their positive terminals are connected together and to one of the points, say A, while the negative terminals are connected together and to the other point B as shown in the figure. In the figure, two cells of EMFs E1 and E2, as before, E1 greater than E2, say, and internal resistances R1 and R2 respectively are connected in parallel between the points A and B of a circuit. Currents I1 and I2 flow out from the respective positive terminals of the cells. They combine as I in the main circuit, such that I equal to I1 plus I2. We name it as equation 1. Let VA and VB be the potentials of the points A and B respectively, and let VA minus VB equal to V. Let us refer to the adjoining figure. We see that V is the terminal potential difference across either of the cells. Now, calculating along the path containing the cell of EMF E1, V equal to E1 minus I1 R1. We call it equation 2. Similarly, along the path containing the cell of EMF E2, V equal to E2 minus I2 into R2. We call it equation 3. Substituting I1 and I2 from equation 2 and 3 in equation 1, we get finally the equation 4, which expresses V in terms of E1, E2, I, and R1 and R2. The combination of the cells between A and B is now replaced with its equivalent cell of EMF E and internal resistance R. Equivalence demands that the current through the cell be I and the potential difference across it be V, such that V is equal to E minus I into R. This is equation 5. A comparison of the equations 4 and 5 yields the equivalent EMF and the equivalent resistance. Equation 6 gives the equivalent EMF E as E1 into R2 plus E2 into R1 divided by R1 plus R2. While equation 7 gives the internal resistance R as R1 into R2 divided by R1 plus R2. Equations 6 and 7 may be simplified as E by R equal to E1 by R1 plus E2 by R2. We call it equation 8. And 1 by R is equal to 1 by R1 plus 1 by R2. This is equation 9. Had the cells in the combination been connected in the opposite order, that is, if the negative of the second cell is connected to the positive of the first, as in the adjoining figure, then also equations 8 and 9 are valid with E2 replaced with minus E2. Now, parallel combination of N cells. It is straightforward to extend the rules for a parallel combination of N cells. The equivalent EMF E and the equivalent internal resistance R of a parallel combination of N cells of EMFs E1 up to En and internal resistances R1 up to Rn respectively are given by E by R is equal to E1 by R1 plus E2 by R2 plus up to En by Rn. This is equation 10. And 1 by R is equal to 1 by R1 plus 1 by R2 plus up to 1 by Rn. This is equation 11. Remark. If a particular cell is connected in such a way that the current leaves it from the negative terminal, then its EMF will enter equation 10 with a negative sign. Equation 11, however, will remain true as explained earlier. This brings us to the end of the lesson 4 of chapter 3. We will become Kirchhoff's rules in the next lesson. Till then, goodbye and thank you.